like I said, I'm just going to record what we're doing here for anybody that is doing this course mostly in an online format or, taking advantage of the Flex. I think there is a review out there kind of in the older videos, but I thought, well, let's maybe do an updated version. Okay, so that's what we'll do today. You guys don't have to see me. I don't have that kind of complex. We'll swap over to the document cam for the most part today. Right, I'm gonna make this full screen for us here in the class, and we'll go from there. So focused. That'll work. Questions for me before we get started here. Let me see if I can straighten this up so it's not annoying me. All right, let me see what microphone I'm using. All right, I'm going to use this one. Check one. That looks like it's good. All right, that way I can yell at you guys and I'm not yelling into this microphone. So I'm yelling at that microphone. I can yell at you guys a little bit better that way. Okay? Questions for me?
Help us go through the last problem additional?
Yeah, absolutely. Let's kind of hold that towards the end, if that's okay. Let's do that. Yeah, I don't mind at all going over the additional problem. But yeah, like I said, let's kind of hold that towards the end. Cool. Okay, let's make sure we're on the same page. So exam 1 for us this semester, that's going to be exam 1. It's going to be Tuesday. Let's see, today is the 15th, so add 5. What's that, the 20th? And so for us this semester, it's Tuesday the 24th. Okay. All right, that's going to be, as we mentioned last time, chapters 1, 2, and then sections 3.1 through, I believe, 3.5. Let's verify. That's going to be basically right before equations of state. Equations of state doesn't show up on this exam. Let's see here. This is in chapter 3. Chapter 3 is on it. Blah blah blah. Let's see here. These are good. I'm looking for section 3.5. Make sure I'm telling you the right thing. We didn't mention reference states, and that's okay. It's not critical for what we're doing. 3.7 is definitely not. 3.6. So yes, 3.6 would start where it's not on this exam. So 3.6 and after that shows up on later exams. We'll need it ready to go for chapter 4 when we get started on that. So that's the reason we'll go ahead and do it for exam 1, but it doesn't show up on this exam. Be able to use property tables for water in R134. That's the basic rules. Okay. So that's pretty much everything up through lecture 6. Be comfortable with those things. As far as logistics, you get 75 minutes. That's a standard class period. We start at, I'll do my best to get us started right at 4:15, but if we start at 4:17, I'll go 75 minutes after that. So if that means we go to 5:32, we go to 5:32. That's perfectly okay. It is open book. Now, if you're in the testing center, let's make sure you've got, if for whatever reason we find you in the testing center, let's make sure you've got a bound copy of the textbook. Okay, so actual bounds. Getting it to where the testing center staff knows what you can and can't use, that's enough of a challenge. So, bound copy of the book. A lot of times I just leave an old beat up 6th edition over there for them in the testing center. That normally gets us. If you're with me, if you've got like a digital copy of the book and you've printed a whole bunch of sheets out of that, and you're functioning that as your book, that's okay as long as it's out of some version of this set of authors, right? Changle and Bowles, and they added Kangaroo here in the last couple of editions. So any edition of Changle and Bowles is fine. And if you want to print material out of any additional chain or voltage, that's fine. You have the same access to the same information, but with that book would have any addition, like we talked about. I have some 9th edition copies. I don't think I've got enough for every single person to have one. I see some books around. I know some of you guys have brought some books to my office, so I think between what you guys have and what I have, I think everybody's gonna be coming. Okay. I've got, I think, 10 9th editions stored away that are in binders, they're loosely. And then I've got my 10th, I've got a 9th and an 8th sitting on my shelf. So we probably got to have everybody covered. Okay. But if you have your own book, bring your own book. You're welcome to put tabs in there, right? You guys have seen mine. I put a tab on there for, this is metric units, this is English units, but put as many more in there as you need. Put the tabs in your book, that's fine. Again, if you want to print stuff out of your book, if you get a digital book, you want to print that stuff, that's fine. Just make sure it's from these particular authors. Let's see what else. One sheet of notes. I know I'm working with engineers here, so I have to specify the units. Otherwise, you guys will show up with 8.5 meters by 11 meters. Up to 8.5 inches by 11 inches. Up to it's standard size A paper, up to 8.5 by 11 inches. You can use smaller, that's okay. It can be front and back. It needs to be your original handwriting. And I've seen I've seen all of your handwriting at this point. I mean, am I going to do a comparison test? No, probably not. What I'm saying there is you could get a lot more information on there if you type it. I get that. Let's keep everybody kind of at the same even playing field. Your original handwriting means whatever you physically can write with your hand on that 8.5 by 11 sheet of paper is okay. That means don't go buy a big poster board, fill it full, scan it, and shrink it down so and print it out on 8.5 by 11. No photocopies, right? It's whatever it has to be your original handwriting, whatever you by hand put on that paper is fine. Front and back. I don't mind I personally don't care so much what you put on there. If you want to put a bunch of example problems on there, I don't mind that. I know you're gonna have some instructors that do. I don't. If you I would suggest to you, if you find yourself needing 30 example problems, you're not studying right. Okay, you really a couple example problems are good. The real goal here of courses, engineering courses at this level, is we want you to learn how to solve problems. Meaning, the hope is we put in front of you some problems that you probably haven't seen that exact problem before. We're testing you on your ability to apply what you've learned, fundamental problem solving technique, and try to formulate a solution for this specific problem in front of you. So having some examples in there to kind of help you remember the steps, or kind of, when you blank out a little bit and you look at this, okay, what did they do here? All right, I can follow some steps like that. That's okay. Again, if you find yourself needing a bunch of examples on your sheet of notes, you really, for your sanity in other engineering courses moving forward, you really want to reevaluate how you're doing your homework. Because that's really the goal of the homework, is to kind of learn how do you solve problems, how do I apply the fundamental principles on these. Anyway, that's just some basic study tips. Do what you got to do to get through this exam, and just like I say, really evaluate what you're doing. Feel free to put examples on. I'm not telling you don't. Okay, I'm just saying it needs to probably be a balance of the equations you think you're going to need, random information that you find yourself using over and over again, and then if you find some examples that you think are pretty common, feel free to put those on. Okay, questions there? Make sense? Supposed to good? Okay, your sheet of notes really should be like, it's one of the best study tools. I found myself a lot of times in college, if an instructor wouldn't let us have a sheet of notes, I'd go ahead and make up a sheet of notes anyway, even if I couldn't use it on the exam. Because what you're literally forcing yourself to do is think about, okay, what do I individually need to know to survive this test? And it forces you to kind of collect that information. And then honestly, once you've gone through that process of figuring that out and committed it to paper, it's a lot more fresh in your brain. It really helps your brain hold on to that information a lot better. Just taking the effort of actually collecting what is so important to me. I need it on my cheat sheet. So anyway, just a nice, my intention is it's there as much, building it as much as a study tool as it is an aid for you when you actually go to take the exam. Okay. All right. Open book, one sheet of notes. What else? Calculator. So we've talked about the calculator a little bit. These are my basic rules. No internet during the exam. All right. No internet. So if I think you've got some calculator looking device that is surfing the internet, I'm going to exchange it for one of mine. Right? Or you're gonna have to very carefully show me what you're doing or stuff like that. It's very rare I've had this, but it's, if I had, I'll put it this way, if I had a room of 100 of you, like a big classroom at a university, you guys are only going to get to use calculators that are approved for the FE exam. So those are scientific calculators, no text entry. They're pretty limited. By the way, it would be really good. It would behoove you to go out and get one of those FE exam approved calculators and start practicing with it. So when you get to the FE exam, your senior year of college, you're used to using that particular calculator that's approved for that. I don't mind you using your TIs, your Inspires, anything like that. I know some of those are capable of some internet capability. If I think you're abusing that, you're in a small enough room, I feel like I can control that. If I feel like I've run into a problem, we're gonna have a different discussion after the exam. Okay. No internet. Make sure you don't have, you haven't jailbroke your calculator and PDFs of solutions manuals. Right. If I think I'll put it this way, if you're face down looking at your calculator and it looks like you're scrolling through a lot of information, we're going to have a conversation about, okay, what do you have on your calculator? Right. It's, if you're doing this right, you don't have to worry about me. Honestly, if you're doing this right, you don't have to worry about me for what I'm watching. Questions here. Does that make sense? I'm trying to be flexible. I feel like in a small class, I can be flexible with you guys. If I had a big class, I'm gonna have to approach this very differently. Okay? Because I'm aware of what is available out there on the internet that you can purchase today. Okay. I've not seen it. It's there's only been just a time or two in the last couple semesters that I've run into it. Yeah, let's have a conversation about your calculator. Okay. If you have questions about your calculator, please stop by. If you're just using a standard TI graphing calculator or a standard scientific calculator, you should respond. Okay. All right. And it doesn't have to be TI, it could be Casio or whatever brand you like. What else? Okay, 75 minutes, open book, one sheet of notes, calculator. Bless you. These are the things. It'll be 4 problems. I have not written it yet. I do not know what those problems are going to be. Most likely, it'll be some kind of manometer or pressure difference problem. It'll be one of them. One of them will probably be two of them would be some kind of chapter 2 problem. So some kind of first law analysis, and then the other one will be some kind of an energy problem or some kind of efficiency problem that probably has some energy involved. So they'll probably like, and I don't know what order they be, and they may not be 1, 2, 3 people in that order. But yeah, one manometer of some type or column of fluid pressure change. One first law kind of problem. One problem that's going to at least involve efficiency and probably some kind of energy. And then the 4th problem will be something from chapter 3. So either something like the add problem or the other problems where you have 2 different states determine some change between 2 states, or it'll be a table fill in a bunch of words like the other problems there. So it'll be one of those 2 types of the 4th problem. So it's, again, don't hold me to that. I'm not putting that in writing. I'm just telling you what I normally put on stamps. I don't anticipate changing that. That's kind of what I go for, but once I get some problems picked out, I'll kind of make sure I'm hitting the learning outcomes that I'm trying to write. Go from there. Okay. No scratch paper. Explain that one. You'll have your test packet will have a cover sheet. Put your name on the cover sheet. You don't have to put your name anywhere else. It's stapled together. 5 pages. Cover sheet with your name on it, and then 1 page for each of the 4 problems. So you can put any of the backs, so the back of the cover sheet or the back of every single problem. You'll have the entire problem will take up on normally something like this at most, at the top of the page. So you'll have the entire bottom of the page and the entire back of that page to work those problems. You have plenty of white space. If you think you need more white space, let me know. I'll get you some blank paper. Why the no scratch paper? I found myself in a situation one time. I got people in the back of the room, and I could not tell how many sheets of notes they had because they were using scratch paper. And you got kind of so no scratch paper, please. There's plenty of room in the test, right? And that way I don't have to keep up with something. My goal is whenever I flip over your cover sheet, if I've got a pile of tests, I'll flip over all the cover sheets and I'll mix them up and I'll grade all the problem number 1s and I grade all the problem number 2s and I grade all the problem number 3s. I don't know who's on grade. That's by design. So if you got scratch paper, it's going to have your name on it. I got to keep up with that, and then I know who I'm grading. I don't like that. Okay. So no scratch paper. That solves a lot of problems there. Plenty of room in the test packet to put your information in. Okay. Make sure you've read the syllabus again about what it says about missing the exam. If you know you're not going to be here Tuesday, you really should have already let me know. But let me know. If we get inside 24 hours, we've got to go with option B. It's not enough time for either of us for me to try to write a different version of the test to put you specifically in the testing center. Accidents happen, emergencies happen. I get that. That's what option B is for. That's if you can let me know more than 24 hours in advance, I guarantee I'll put you a version of the test in the testing center. I should be able to keep it about the same level, equal difficulty as everybody else in the classroom. The more leeway, the more lead time you can give me, the more I can guarantee whatever I put in the testing center for you is the same difficulty as what everybody else gets. The closer we get, the harder that is for you to do. Right now, it's early enough. I can pick problems that I could ask 3 or 4 different ways, right? And really kind of guarantee some uniformity. Once I've got that test written, I can do that, but it's a little bit harder. So anyway, if you want option A, that means I need at least 24-hour notice. More is preferred. So if you know you're not going to be here Tuesday in class, let me know in advance, please. Okay. Those are the basics. Those are the logistics. I'll put the clock on the board here in class. If you're in the testing center, you'll need to keep track of your own time. You lose points if you go over the prescribed limit. Okay, so with you guys here in class, I keep track of your time for you. So I put a clock up on the board, right next to it. You know what time we're going to stop at. I'll let you know when we're about halfway through. I'll let you know when there's 5 minutes left. If anybody's still working, I'll let you know when we're down to the last 60 seconds. Yeah, that's how that works. So that's what that'll look like. And honestly, that's pretty much how all the tests will look. I try really hard to not make any major adjustments from one exam to the other. Once you kind of understand how my tests work, you understand how my tests work, and that's by design. Okay. Cool. And if there's no questions about logistics, let's talk about topics then. Something that says exam 1 review. Okay. All right. 2 of something. You want to review. Okay. Topics. Chapter 1. Get my notes here. You probably do it from memory, but then I'll probably forget something and everybody will be mad. Well, let's not do that. Chapter 1. We talked about a handful of things. We talked about dimensions and units. As you guys are starting to see, those are going to be the bane of your existence in any thermal science course moving forward. Units, making sure your units line up. Fortunately, nobody's asked me this semester, hey Steve, how do I convert PSI to BTUs? Because the answer is you don't. Those are different dimensions. You cannot convert different dimensions to the same units. It doesn't work. How do I convert kilograms into hours? No, you can't. Those are not the same. Those are different dimensions. One's time, one's mass. BTUs is energy, PSI is pressure. Those are different dimensions. But if the dimensions are the same, I can get the units to line up. I just have to throw enough unit conversion factors at them. We started day one and we said, here's a nice conversion for that. For every pound force, second squared, there are 32.2 pound mass feet. That is a common unit conversion factor you will use in many courses after this one. Anytime you're working with a text or a subject that works with pound mass, you're going to need to know this conversion factor. Okay, what else do we talk about?
Will we be allowed to have the sheet that's on the back of our books?
Yes.
The conversion?
Yes, yeah, the conversion factors in the inside cover of the back of your book, I consider that part of your book. Again, if you find yourself in the testing center, make sure we work with me about getting a hardbound copy of the book. So I try to minimize how much those testing people staff have to know because they don't know what this stuff is, right? I try to minimize how much we have to communicate to them. Yes, this is okay. No, that's not okay. So as long as you're in class with me, anything that comes out of the book, I'm fine if you have it. Good question. Yeah. So we talked about, also we mentioned systems. We said there are closed systems and control volumes. What's the difference?
System, there's no change in mass.
Right. Right. It's closed to mass flow. Where a control volume is just a region in space where there's probably mass flowing through it. And for our purposes in this course, a control volume is going to have mass flowing through it. We're a closed system. If they tell us it's a closed system, that means the mass is constant. There's no mass crossing the boundary. So a system is essentially, again, anything I can draw a dotted line around is one way to think about it. It's anything that I can isolate from its surroundings through either a real or imaginary boundary. And from there, then we talked about properties. Properties are basically a dimension for our system. It's something we want to measure or describe for our system. And in chapter one, we focused on temperature, volume. Within there are our friends here, specific volume. Again, is lowercase v, that is total volume per unit mass. And its cousin, the density, which is the reciprocal of specific volume, mass per unit volume. We also talked about pressure. We said that there is a pressure, we will experience or observe a pressure change in a column of fluid. So for a single fluid, if I move down to a lower location, a lower elevation within that fluid, I will see a pressure increase if I move down in a fluid. So this pressure change is equal to essentially rho g. It's essentially the weight per unit volume. Again, density is mass per volume, multiplied by gravity, that gives me weight per volume. In a fluids text, a lot of times they'll call rho g, they'll call it gamma, they'll call it a specific weight. This text, I think, occasionally mentions it, but we don't really refer to it much here. Rho g is just fine. This is the weight per unit volume is what that is. And you multiply that by the change in elevation. If this is 2 minus 1 on this side, your text says Z1 minus Z2. And again, we had a kind of a discussion earlier. That means this Z value is referring to the elevation. So what we're saying there is if I increase my elevation, I decrease my pressure. Or if I decrease my elevation, if I increase my depth, it will move down in the column of fluid. So if I decrease my elevation, I'll see an increase in pressure. And so again, this equation will get you for one column of fluid. If I've got something where I've got multiple columns of fluid, for me, the simple way, because it's fewer things to remember, I just write an equation for each column of fluid, right? This equation for each column of fluid where the density changes, and I just need to know the elevation of each different points within the column of fluid. So I need to have some Z value where I say maybe some Z value is 0 and measure all elevations above or below that. You're welcome to. There are methods. If I've got a multi-fluid system, there are methods where you can go through and write a single equation. And if I've got something on this end, I want to know the pressure on this end. Well, I can say, well, start with the pressure here, add anything that goes down, subtract anything that goes up, and add more going down, and subtract going up, and that equals the pressure on this end. If you're okay, like if you're good at memorizing rules and specifics and stuff like that, and you want to memorize all those rules for writing a single equation, go for it. That's fine. I have no problems with that. I don't do this often enough to memorize all those rules. This one's pretty easy to remember. This gets me one column of fluid. Know what the density of the fluid is, know what the Z values are within that fluid, write the next equation for the next column of fluid, et cetera, et cetera. But if you're cool with combining them into a single equation, that is fine with me. It does not bother me at all. I just know my brain has got too much other stuff going on to keep up with. That's just work. Do what works for you. Those are the things in chapter 1. Right. And I want to get to where we can at least look at the ad run there at the end, but if there's questions here, we can entertain those. Like I said, do be prepared for some sort of use of this equation. It might be a manometer, it might be, a lake with mercury contamination in the bottom. There are a variety of ways that we can use this equation a couple of times. Be ready to implement this equation. Oh, one more thing. It's not uncommon that I'll ask you about or ask you to interpret gauge pressure. Remember, gauge pressure is equal to the difference between absolute and atmospheric pressure. What that means is, if we go out, we talked about, if I take a gauge and I put it on my tire right now, I've got a gauge in my glove box. I go put it on my tire because my tire looks low, and my gauge gives me a reading at 20 psi. That's a little low. Right? Gives me a reading at 20 psi. It's not saying that the pressure inside the tire is 20 pounds per square inch. What it's saying is the pressure inside the tire is 20 pounds per square inch higher than the pressure of the atmosphere outside. It's giving me the difference between the two. The gauge is going to give you the difference between the pressure inside, the absolute pressure inside, and the local atmospheric pressure outside. So you'll want to be ready to interpret that. I know at least one of the homework questions asks something about absolute versus gauge. I always try to include at least one question that's got something that has to do with that. What else then? So really, it's chapter 1 is this is kind of the meatiest mathematic part. As long as you understand some basics of units, and be prepared to wrestle with PSI, density in pound mass, and all the joy that goes along with that. Sorry to be the bearer of bad news. That stuff doesn't ever go away. All right, what else here? Chapter 2. By the way, I normally don't come in with a lot of times what I do in a review, I'll do kind of like what you're seeing here. I'll go through, hit some of the highest points, kind of do a skeleton outline of the material. And what a lot of people find is that we've seen the theory in class. Maybe we do an example or two in class. You wrestle with the theory in some homework problems. And then now we kind of come back and we look at the theory one more time from a slightly different perspective, but now with a lot more experience on board. We've already wrestled with it. That kind of helps solidify everything together a lot of times. So that works for a lot of people. It doesn't necessarily work for everybody. But that's normally what I do. And again, I try to allow time. You guys have questions, try to address those and work those. Very rarely do I come in with example problems that I'm going to work during a review, but if you have ones you want me to look at, happy to do that. So, chapter 2, keep that in mind. What do we do in chapter 2? Chapter 2 focuses on energy. We talked about energy being, if I combine a whole bunch of energies together, I use a capital E to do that. I can use a lowercase e to represent energy per unit mass. So mass times a lowercase e gives me a capital E. That's common nomenclature. That's common structure that we'll use a lot of times in most courses like this, where we use a lowercase variable to represent the quantity per unit mass. Another common thing that we'll use in a lot of thermal science courses that we introduce in thermodynamics is the concept of rates. Energy rates. So anything that I put a dot above means that that is a rate. It's being measured per unit time. So E dot, energy per unit time, or the rate of energy transfer, is going to equal M dot, the rate of mass flow. It's mass per unit. And if I multiply M dot by energy per unit mass, if I know how much energy per unit mass something has, and multiply by the rate at which mass is carrying that energy or flowing through it, that gives me the rate at which energy is being transferred. All right. And then we talked about M dot, mass flow rate. A variety of ways we can find that. Common way is density times V dot, where V is volume per unit time. Again, V with the cross on it is volume. So density times volume per unit time will give me mass per unit time. I can take that same density, and instead of volume per time, I can take the product of area times speed, the average velocity. So we know the average speed at which particles are flowing through a cross-sectional area. The product of those two gives me volume per unit time, the volumetric flow rate. And again, remember, specific volume is the reciprocal of density. So everywhere I have density, I can put 1 over specific volume, vice versa, with the same equation. Okay, so, and we talked about this a few times, have some way of knowing which V you're dealing with. Are you dealing with speed, volume, or specific volume? Occasionally you'll deal with voltage, but that is fairly rare. Okay. We talked about different kinds of energy. What are the types of energy we talked about? Kinetic. What else? Potential. What else? Internal. Absolutely. 3 more. Well, 2 more. What are the ways it crosses the boundary? Excellent. Yeah. What are those? Heat, heat and work. Those are my external energies. Yes. Heat, we use letter Q. Internal energy, we use capital U. These are the types of energy. So we work our way up through here and we talk about, in chapter 2, they did talk about different types of work. Talk about different kinds of work. Some of the main ones that we will encounter throughout the rest of the semester are electrical. Electrical work occurs when you've got electrons flowing. That causes a force, magnetic force, that we can harness to do work. And so your electrical power is going to be what we call voltage times time. Your electrical work, so if this is the rate of energy, to find the total amount, I just need to integrate the rate with respect to time. How do you find the distance traveled? Well, you integrate your velocity with respect to time. That gives you the distance traveled. Same thing here. This is a rate. Integrate the rate with respect to time, I get the total amount. If you have what we call DC, right, that is constant V and I, and voltage being V, current being I. So if I have what we call DC conditions, it's constant voltage, constant current, then your electrical work is very simply your electrical power multiplied by the amount of time over which it occurs. In this country, we sell electricity in what we call the kilowatt hour. So a kilowatt is a unit of power. It's W dot. And the hour then is the amount of time. So a kilowatt hour is, we're transferring energy at a rate of 1 kilowatt for an entire hour. It's 3,600 kilojoules. We mentioned the spring. I'm not going to put a spring problem on the exam. I'm just mentioning it though, because it does show up from time to time. Your work from a spring is going to be your spring constant divided by 2 times basically your change in your X value squared. So again, I'm not going to put that on exam, but if you're working some homework problems, you might see an occasional spring problem where they've stored some energy and they want to know how much work the spring does or something. Okay. A lot of times our work term is just a quantity that's given to us, or I'm using the first law to solve for. But depending on what homework problems you work or what additional problems out of the book you work, you can encounter different kinds of work. And we'll see electrical work throughout the semester from time to time. So it bears repeating. Okay. I think that brings us up to the first law. So there's really kind of 2 meaty parts of chapter 2. One being the first law. The first law tells us that the energy in minus the energy out equals the change in the energy for my system. And we already said earlier, we have different kinds of energy. So the ways that energy can come in, bless you, could be heat in, could be work in. And if you have mass crossing the boundary in a control bond, energy of mass coming in, and then all these things going out, minus Q out, minus work out, minus any energy of mass going out. I'm going to run out of room, so I'm going to write on the second line. That's all going to equal then your change in the energy of your system. Well, the system can have its own kinetic potential or internal energies. So change in internal energy plus a change in kinetic energy plus a change in potential energy. That's the entire first law. What we'll see as we move forward, we're starting to see it now, as we'll see it more as we move forward, very rarely, you're never going to use all those terms in one problem. You'll use more or less, depending on what kind of system you're working. Okay, so the escalator problem. We had people, we were putting work into them from electricity, and we were changing their potential energy. That was it. Just a handful of terms show up in that one. All right. The other meaty part, so to speak, in chapter 2 is this concept of efficiency. Efficiency is something you'll experience and work with throughout many of your courses moving forward. A lot of times, thermo might be the first time we introduce it. In your text, they like to, and by the way, we almost always use the Greek letter eta to represent efficiency. In your text, they really like this idea of output over input. And that's okay. That works about 95% of the time. I always suggest to you, think about what do you expected small value by your expected larger value. All right. If you've got something that its sole purpose is to provide output over input makes sense. So take your phone charger, for example, right? Take your phone charger. Your phone charger is going to put less electricity into your phone than the electricity it's consuming out of the wall. How we know that is because it's putting off heat. That energy has to go somewhere. Not all the electricity coming in goes as electricity out. Some of it's getting emitted as heat. Not all of it makes the process. The efficiency would be the ratio between the two. You can go back over here and say, well, here's how we find that amount of electricity, voltage times current times time. Will give you both the output and the input for that device. Again, remember, efficiency is a value that's going to go from 0 to 100%. It needs to be unitless, meaning it has to have, it's a ratio, so it has to have the same units top and bottom. So the real critical part is making sure you're comparing energy to energy or power to power or whatever it is you're trying to compare, to make sure your dimensions are the same top and bottom, because the true efficiency needs to be unitless. Okay. It's a big thing. I've got a few other notes down here. Adiabatic, what does that mean? No heat transfer. Yes, no heat is crossing the boundary. That. Let's see. These are the big ones, right? Being able to kind of look at what the problem's asking about. If the problem's asking for efficiency, a lot of times it might say, well, what is the purpose of the device? Calculate the efficiency. If you look at the add problem, determine the efficiency for increasing potential energy. I'm telling you what the output is. What is this device supposed to do? It's supposed to increase the potential energy. So kind of think about what is the purpose of the device, or what do I expect this device to, if I'm comparing two quantities, what are those two quantities? Which of those two quantities do I expect to be smaller? I expect this device is going to require more than the theoretical minimum that should be required. So it's really one of the first times maybe you've been really asked to think about, okay, there's not really a formula for this. It's just a concept. You have to think about how you apply it. But that's really a lot of what we're trying to teach you guys how to do in engineering. Okay, chapter 3. I'm not going to go super in depth in chapter 3 because you guys just finished up a pretty good homework on that. But the basics here. Using property tables, we said there's a process. Might be a good thing to write on your sheet of notes. I'm probably not going to get it exactly right. Okay. Determine your substance, or identify your substance. I'm going to get the general idea right. record known properties. For R134 and water, I'm using those tables. I need at least two. That can be pressure, specific volume. I keep writing you. Pressure, specific volume, temperature, internal energy, enthalpy, or entropy. Need at least two of those. If they tell me sometimes they'll tell me the phase, and that counts as a property. Like they might say you have saturated liquid. Okay, that counts as a property, because then all I would need to know is the pressure or the temperature. I know exactly where to go on the tables. So you'll see that throughout the semester. But right now we're really probably given two of these properties. We have to figure out what do we do with the rest of them. That's step 3, is basically what the heck do I do with these properties I've just been given. And the goal there is to determine the phase, is the technical way to say that. The layman's term is what table and then what row. Or if you're between rows, what rows are you between? What table, what row? Zoom. Determine the phase, what table, what row, or what rows are you between? To do that, of course, you got to be aware of your units. Make sure you're using the right table, the right substance, for the right units. And then ultimately, you're really after this is state. This technical way of saying is determine the state, because here you're actually determining the phase, which is a whole nother subset we'll tackle in just a second. And the last step is record desired properties. Right? Once you know what row you need to be looking at, then you can just record everything on that row if you want, if that's your desire. It's not going to be what's required, most likely. Most likely, you probably just need one or two of those properties. If you desire to record all of them, you can. You probably just desire to record what's needed. Just make sure you know what's needed, right? What is the problem asking for? What properties do I need to actually get me to whatever the problem's asking for? That's what you need to be concerned about at this point. You get to step forward. Now, we talked about determine the phase. That takes one of two forms. If I'm given pressure or temperature as one of my two properties, remember, I need at least two properties. So if I'm given pressure or temperature as one of the properties, and I'm given V, U, H, or S as the other property, this is the first scenario. Then I can draw this diagram. P or T, I have my given value. At that given value, I go to the saturation tables, and I'm looking up 2 points, because I'm going to compare my V, U, H, or S value to the value for that substance for a saturated liquid, and the value for saturated vapor. That's what I'm going to find in the saturation tables. And I'm looking to see, is my V, U, H, or S, whatever I'm given, is it between these two? If it's between these two, I have a saturated mix. If it's over here, I have a superheated vapor. If it's over here, I have a compressed liquid. The other scenario, very common scenario, given pressure and temperature. So this diagram would work for any combination. There's like 8 different combinations there. The one it doesn't work for is given pressure and temperature. And you might ask, well, what if I'm given V and U? And we don't really have a solution for that. But if I'm given pressure and temperature, I can draw this diagram where everything over here is liquid, everything over here is vapor. And at your given pressure, you can go look up your saturated temperature. If you've exceeded that saturated temperature, you're in the vapor region. If you've not met that saturated temperature, you're in the liquid region. Follow appropriate rules. If you're in the vapor region, go to the superheated vapor tables. If you're far enough into the vapor region, if it's something like carbon dioxide or air, you could use ideal gas law, which again, that's not going to show up on this exam. Show up later. If you're using ideal gas law on this exam, you're probably doing it wrong. We're just going to deal with water and R134 this time. Let's see what else. For liquids, V is approximately V sub F at the given temperature. Same for U, H, and S. It's an approximation. If you're at a really, really high pressure and you've got a compressed liquid table, we do have a compressed liquid table for water, but it's at very high pressures. You probably won't use it because they're very, very high pressures. But if you have a very high pressure and you have a compressed liquid table, it might be handy. If not, if it's R134, if it's low pressure water, just use this. Once you establish it's liquid, you ignore the pressure. Once you figured out your liquid, use the pressure here. And once you figured out your liquid, use the temperature and temperature alone. Go find your V, U, H, or S, whatever you're looking for. And of course, if it's a mix, we need to figure out the quality. The quality tells us how much is in the vapor phase. And we find that by the known property, in this case, maybe V, minus the value for saturated liquid, divided by the difference between the vapor and the liquid value. Same thing for the other properties. And the goal there is you'll have one of these four, either U, H, S, or V. You'll have one of those four. You use the one that you have to find the quality, the amount that's in the vapor phase. Once you know how much the quality is, you use this expression and the other versions to find whatever properties you need. The F and the FG values and the G and the F values are just table properties we go look up. All right. Wanted to see the add problem. So I want to share screen. So it's a request to look at chapter 3 add problem. So let's go through them. Write this information down. Go back to the full screen on the paper. All right, so this is page, what was it? Page 4, this is page 5, this is page 6. All right. So givens. R134A. I have an initial temperature, 0 degrees C. And a mass, 200 kilograms. I have an initial pressure, 400 kilopascals. Says the pressure remains constant. the final volume 0.5 meters cubed. I know it's capital V because that's not per unit mass. It's not meters cubed per kilogram. That's just meters cubed. That's a total volume. They want us to find delta. We could either find, they didn't specify, we could find total internal energy change or the specific internal energy change. Either one. Actually, well, yeah. So what do we need to do? Well, we need to find U values. U values are going to be properties. So I'm going to need to use table properties here. How do we do that? Said earlier. Determine the substance, R134, that's known. Record known properties, I need at least two. Well, I've got two different states here. So I do know pressure and temperature at state 1. I know pressure at state 2, and I know total volume. Now, total volume doesn't show up on the tables. What does show up on the tables? Specific volume. Specific volume shows up on the tables because that way it doesn't matter how big the system is. The table describes any system because I'm describing per unit mass. It doesn't matter how big my system is. So the tables use specific volume. So I can find, but I do have the mass. So I can find the specific volume at state 2, and I know the pressure. So I know two properties at both states. So I've recorded the properties. I know at least two at each state. Now I need to figure out my state, which basically is saying I need to know which table, which rows I'm using. To do that, I need to figure out the phase. So here's how you do that. Well, state 1, I know pressure and temperature. So I need to draw this diagram. Who has their book? Can you tell me the saturated temperature of R134A at 400 kilopascals? What was the saturated temperature of this one? 8.91. Those are C's, yes? C's. We have 0. That puts us back here in the liquid region. Puts us back here in the liquid region. So given P1, 400 kilopascals, T1, 0 degrees C. That tells me that at state 1, well, what do I need to know at state 1? I need to know U1, okay? U1 is going to equal U sub F at 0 C. So go look that up. Okay. We said at state 2, I know P2, and I know specific volume 2. Because specific volume 2 is going to be volume 2 divided by the mass. What is the specific volume at state 2? It's 0.5 divided by 200. What is it? 2 zeros and 2 5? Like that?
Yeah.
Okay. Thank you. Okay. So state 2, we have this diagram. I have pressure, and I have specific volume. So I need to know where I am on this diagram. So I need to go look up the F, G values. Bless you. Just give me the first 2 digits here on the F value, if somebody would. So yeah, how many zeros here? 3 zeros, and then what? 7, 9. Okay, roughly. And then what about the saturated vapor value? What are the first 3 numbers on that?
0.51.
Like that? Okay. We are here, right? Tells me I got a mix. Since I have a mix, I need U2. That's what I'm after. All right, that's what I want. I've already got U1. I need U2. Well, to do that, because I'm in between, I need to figure out the quality. So that means U2, which is what I'm looking for, is going to be UF divided by UFG. I don't know the quality, but I can use these values down here. V2, which is known, minus VF, divided by VG minus VF. That would give me the quality. Quality gives me U2. Take the difference, multiply by mass. Good to go. Question? Just strikes me. I'll post this YouTube video. I'll post this video to my YouTube channel, but then I'm gonna have to after this exam, I have to trim this part out. That's okay. I'll do that. If I decide, and that's if I decide to use this add one problem in the future, which I may not. Got some old test problems. I might retire and use those as add one problems.
I got a value of 0.003.
Oh, you got for the X?
Yeah, quality.
Yeah. Okay. So then we can use that. We'd have to go back and look up these values then at 400 kilopascals, and that'll give you your U2. We can go from there. Okay. I'm not going to work it all the way to a solution. Point us in the right direction. Other questions, comments, complaints? All right, I'm gonna turn you guys loose. I'm happy to stick around for another minute or two. That's what I got, guys.